Starting at the very bottom of the spaceflight ladder is the chemical rocket. It is nothing more than a controlled explosion. We rely on solid rockets, essentially giant Roman candles that cannot be turned off once ignited, and liquid-fueled engines, which burn a hyper-pressurized mix of propellants. They are loud, brutal, and incredibly inefficient. This brings us to the ultimate nightmare of space travel, the tyranny of the rocket equation. To launch something into space, you need fuel, but that fuel has mass. To lift that extra mass, you need even more fuel, which requires even more fuel. By the time a chemical rocket sits on the launch pad, 90% of its total weight is just explosive liquid, meant to lift the remaining 10%. They are terribly slow, absurdly expensive, and completely trap us within our local cosmic neighborhood. It took the Apollo missions 3 whole days just to reach the moon using this brute force of fire. If we want to go anywhere deeper into the solar system without waiting a lifetime, we have to stop burning things. But to go further into the deep, dark void, we do not need fire. We need the eerie blue glow of quantum physics. Enter the ion thruster. Instead of igniting chemicals, this engine uses solar panels to generate electricity, stripping electrons from a heavy gas like xenon. It then shoots these charged particles out the back at over 90,000 miles per hour. But here's the catch. The actual thrust produced by an ion engine is pathetically weak. If you hold a standard coin flat in the palm of your hand, the downward pressure you feel is exactly the same amount of force an ion thruster generates. You could not use it to lift off from Earth, but in the frictionless vacuum of space, it is a marathon runner. While a chemical rocket burns out in minutes, an ion engine can fire continuously for years. Over time, that tiny force compounds. The Dawn spacecraft used ion propulsion to steadily accelerate to a staggering 25,000 miles per hour, chasing down asteroids with pinpoint precision. Yet even ion drives need to carry heavy tanks of xenon gas. But what if we completely abandon the idea of carrying fuel? The next engine does not need heavy tanks at all. It comes from the stars themselves. Welcome to the solar sail. In the vacuum of space, light actually has momentum. When photons from the sun hit a highly reflective surface, they bounce off and give that surface a microscopic push. If you build a sail thinner than a human hair, but large enough to cover a city block, you can ride this ocean of radiation indefinitely. It is exactly like sailing a ship on Earth, but instead of wind, you are catching the literal rays of a star. There are no moving parts and no massive explosions. While it starts out incredibly slow, it never stops accelerating as long as light hits it. And we do not have to rely just on the sun. The Breakthrough Starshot initiative plans to blast microscopic solar sails with giant Earth-based lasers. This focused hurricane of light could accelerate a tiny probe to 20% the speed of light, reaching our nearest stellar neighbor, Alpha Centauri, in just 20 years. But there's a massive problem. You cannot push millions of pounds of steel and human cargo with a fragile mirror. Solar sails are great for tiny robots, but if we want to send actual humans to Mars, we need to wake up the terrifying power of the atom. Enter nuclear thermal propulsion. Instead of mixing 2 liquid chemicals together to create fire, this engine uses a nuclear fission reactor to brutally heat up liquid hydrogen until it violently expands and blasts out the nozzle. Imagine replacing a standard campfire with a miniature hyperactive star just to boil a pot of water. The sheer thermal violence of the reactor shoots the propellant out at mind-bending velocities. During the Cold War, NASA actually built and successfully tested these monsters under Project Nerva, and the results were phenomenal. A nuclear thermal engine is roughly twice as efficient as the absolute best chemical rocket we have today. This is the ultimate Mars Express. Using this atomic brute force, we could easily cut the travel time to the Red Planet in half, saving astronauts from months of deadly cosmic radiation exposure. It gives us the heavy lifting capability of traditional chemical rockets, but with double the mileage. However, firing up a live nuclear reactor on a terrestrial launch pad makes governments incredibly nervous. If a standard rocket blows up in the atmosphere, it's a tragedy. If a nuclear thermal rocket blows up, it rains down radioactive debris across continents. So, engineers have largely buried this concept until we're already safely up in orbit. Nuclear thermal reactors are incredibly powerful, but back in the 1960s, scientists dreamed up a machine that was infinitely more insane, riding the shockwaves of atomic bombs. Welcome to Project Orion and the concept of nuclear pulse propulsion. Instead of gently heating hydrogen, this spacecraft literally drops small nuclear bombs out of its rear exhaust. Fractions of a second later, the bomb detonates, and the resulting thermonuclear shockwave violently slams into a massive, shock-absorbing pusher plate attached to the bottom of the ship, propelling it forward. It sounds like absolute madness, but mathematically it is flawlessly brilliant. You are essentially taking a massive steel skyscraper and hopping it across the solar system by repeatedly nuking it from below. Because the explosions are external, the ship can be unimaginably massive, weighing thousands of tons, complete with heavy radiation shielding and entire cities of crew members. A nuclear pulse ship could reach Saturn in a matter of months rather than decades. The only reason we are not flying these atomic behemoths today is the 1963 Partial Test Treaty, which rightfully made it highly illegal to detonate nuclear weapons in space. But fission bombs are the brute force weapons of the 20th century. If we truly want to become a star-faring civilization, the next engine must mimic the exact core of the sun itself, or perhaps something much darker. First is the fusion drive. Instead of splitting heavy atoms apart, this engine forces light elements like hydrogen to smash together and fuse, releasing an apocalyptic amount of clean energy. It is quite literally bottling a living star to use as a thruster. A fusion rocket could comfortably accelerate a ship to 10% the speed of light. But if that is not fast enough, you must harness the most volatile substance in the universe, antimatter. When normal matter and antimatter touch, they completely annihilate each other. Unlike nuclear reactions that only convert a tiny fraction of their mass into energy, antimatter annihilation achieves a flawless 100% conversion rate, exactly as Einstein predicted with E equals mc squared. The energy output is completely incomprehensible. You would only need a few dozen grams of antimatter to propel a manned mission to Pluto in just a few weeks. The problem? Antimatter is ridiculously difficult to contain and currently costs trillions of dollars to manufacture just a single gram. All of the engines we have looked at so far obey the strict laws of Sir Isaac Newton. You throw mass backward to go forward. But to actually break the cosmic speed limit, the ultimate machine cannot move through space. It must violently warp reality itself. One theoretical endgame is the Kugelblitz drive. By focusing unimaginably dense lasers onto a single microscopic point, we could create an artificial pocket-sized black hole. We would trap this microscopic singularity in a magnetic cage and feed off its intense Hawking radiation, granting us a near-infinite energy source. But the absolute final boss of propulsion is the Alcubierre warp drive. This engine does not produce thrust at all. Instead, it uses massive rings of exotic negative energy to compress the fabric of space-time directly in front of the ship, while violently expanding the space behind it. You are not moving. You are encasing the ship in a bubble of undisturbed physics and surfing a literal wave of warped reality faster than the speed of light. This is the ultimate limit of physics. Subscribe to Starlight for more deep dives into the cosmos.